Hello? Do you hear me? People in the last row, can you hear me? I can't hear you, so okay. Much better. Okay. Wow. Before I get too excited, I gotta tell you this. Like, Rafał, like my bio, I wrote it. This is supposed to be like huge laughter right now. Like, speakers get to write their own bio. I could have said Andrei is an awesome guy, and he would have just said that. So take it with a grain of salt there. Okay. It's a huge honor to be here. I have to confess I didn't expect this. When I got contacted by the organizers, I thought, okay, so these folks at Nokia are having 50 engineers kind of thing. And yeah, okay, I'll come, no problem. And now it's like 500 people in here, and it's a huge honor to be here. Wrocław is an awesome city and a very good university and technology hub. So I learned, and I was very pleased to see that. And it's a huge responsibility as well. I mean, imagine I teach you the wrong thing. Like, you know, it could make for a bad quarter for Nokia, right? It could have like a huge impact on the local economy here. If maybe I teach like global variables are awesome. Use them. Look, you know, they're good. So, well, I also have to confess I'm reaching a personal record right now. I'm very proud of myself. This is like my biggest slide ever. Never had. This is like awesome. Like by far my greatest slide. All right. This does work. So just to make sure I'm in the right place, quite honestly, who's here a programmer? Like just writes code for a living? Okay, most hands. Who wants to write faster code? Okay, we're in the right place. And you know, before we get into things, how much did you pay to get in here? 0, right? Okay, so make sure you may get what you paid for, okay? So don't raise your expectations all that high. All right, so I want to talk about writing fast code, but before you know what you want to make faster, you know, there are a number of things that I shouldn't be even speaking about because they should be obvious, but they're not. So number one is you need to make sure that you keep Amdahl's law in mind. And Amdahl's law goes, improvements in a large system built of many components, if you improve a part of it, if you make one faster, essentially that's going to be weighted by the participation of that component in the system. And Amdahl's law is not particular to programming or to efficiency. It's a universal law, essentially saying that if you improve something that has 10% contribution to a system, then the best you can get is 10% improvement overall. Make sense? It's quite obvious, but you know, if you gotta essentially many of us, and you know, fess up here. This is group therapy here. Fess up. Many of us have worked on improving the parsing the command line option, which is like, you know, like 2/1,000,000th of the running time of the program, right? Who's here optimized that kind of stuff? All hands should be up. I'm not kidding, right? Optimize a part of the system that's not really you know, it's not a big contributor to the time of the runtime of the system. So it's essentially here that you want to keep the Amdahl's law in mind so you know what you want to optimize and more specifically what not to optimize. These are very important things to keep in mind because otherwise you end up working a lot on essentially like nothing at all. So collect application profile data before considering optimization and focus on optimizing the top consumers of time. Now, there's another law that I like to call Ladman's law. So Amdahl was a real guy, right? So Amdahl, like this guy, sorry. this guy, okay, you don't see this, right, do you? Is it visible? You don't want to do that, okay? I was kidding. So Amdahl's was a real guy, but Ladma is like Amdahl spelled backwards. It's the converse of Amdahl's law. Essentially, you want to optimize components outside the whole application because that makes for a much faster turnaround. However, systems are complex enough that you want to actually profile again within the application after you optimize the component. So Amdahl's law, choose your components wisely to know what to work on when optimizing. And Ladma's law would go optimize outside the system, retest within the system. Sometimes that's not possible. Like at Facebook, we have this large hack compiler, and each % of improvement in the compiler meant essentially a lot of money in terms of power consumption and provisioning. So 1% would be actually would be a lot of money over the months and years. And it turns out if you want to optimize a large system by 1%, it's very difficult to take components out and optimize them separately. So that makes for a completely different turnaround, much more unpleasant to optimize, much more noisier too. So make sure you do this. And, well, there will be a discussion here. So, as I just said, doing the whole application benchmarking is difficult, but optimizations do have global effects because they use components in a system that are shared across the whole large system, such as the cache and the memory. So it's virtually impossible in today's machines to make sure that you optimize something outside of a large application and then put it back and make sure you have the same optimization. So the effectiveness of micro-benchmark decreases with the margin that you're looking for when optimizing. All right, well, if you're old like me, you remember the Zilog Z80 days? Who knows about Z80? Spectrum, Sinclair Spectrum? A few reluctant hands come up slowly. And from those who I don't care about admitting my age kind of people. Very nice. So in those days, it was very interesting because you could deterministically tell how fast the program is going to run. You could look at the listing, and you could say, you know what? I can count the cycles, and I know exactly how long this is going to take. And who knows why? You got to shout. So just shout. Why? Give me like sound bites. I don't know. For example, no cache. I just gave you a good one, actually. Right? So, anything else? No pipelining. Thank you. No branch prediction. There's essentially like every answer starts with no. There's no pipelining, no cache, no branch prediction, no speculation, single-threaded, no multi-threading. Awesome. I get to put it with a no in front. No wait states. Every memory access was in one cycle, right? So it was very deterministic architecture. Well, those days are gone forever because essentially ever since then, CPU architectures have gotten better at optimizing the average runtime at the cost of determinism. There's speculation. All of these, those with no in the front, right now they have yes in the front, yes cache, yes speculation, yes everything, yes pipelining, yes stalls. So it's not only cache, but it's a whole hierarchy from the moment the CPU asks for a byte of memory all the way to the memory itself. There's a number of levels of caching, some local to the CPU, some shared, that all are kind of contributing to the complexity of the thing. So, okay, great. So I hope I convinced you that today's computing architectures are very complex and impossible to deterministically predict in terms of speed of execution of a specific piece of code. Not to mention, things like interrupts. All modern operating systems have interrupts that are not maskable, and multiprocessing, bus contention, and that kind of stuff. even like dynamic frequency control, you can't count on cycle duration being the same across an execution of a program, of a trace. So it's that all of these make virtually impossible to get identical timings for the same code, which is weird. Okay, so to bring this home, let's discuss intuition a bit, because we all have a lot of it, don't we? And we have intuition about, oh, this is going to be fast, this is going to be slow, this is going to be easy, this is going to be hard, etc. So intuition is like your worst enemy when you want to optimize software. So it's about the worst thing you can rely on, because most intuition is dated, it's simplistic, not simple, simplistic, meaning it ignores a lot of complicated things, trying to provide a simple explanation. People judge in patterns and things that are simplifying a complex reality, and this simply doesn't work for CPUs. So, and we have like all of this folklore that goes around, and people talk about it around the office, and oh, that guy is smart, you must know. For example, I don't know, this one. Fewer instructions means faster code. Can anyone imagine a case when actually that's not the case? Fewer instructions means faster code. Why don't you yell at me a few sound bites? Why do you think that's not the case always? Lots of jumps. Okay, yeah, you can have like smaller code, but a bunch of just unpredictable branches. Huh? Cache misses. Yeah, so even if the code is small, it could make cache misses all over the place. Let me give you simpler ones. For example, there's an instruction that counts the bits in a byte, or in a word. So it counts the bits, it's log 2 of the word. And it's a 1 byte instruction, it's real like compact. And it doesn't have any jump, and doesn't have any cache misses, because it takes a register. And it turns out that on some CPUs, essentially that one instruction kind of has microcode inside and does things, and it's complicated inside. So it runs a little program inside the CPU. Turns out on some CPUs, that's slower than the loop that you write by hand. So that's terrible. All right. So, well, okay, so we mark red whatever is not always true. But before that, lest Nokia has a bad quarter, let me add this. In the long run, fewer instructions are going to lead to faster code. It's a good proxy. It's not perfect, but it's a good proxy. It's a good estimator. It's a good feature. So if you kind of keep on cranking the instructions down, at some point, the code is going to get faster. So it's a good envelope for it's a good proxy for measuring speed. So make sure that fewer instructions are not always faster code, but in the long run, they're going to, there's no other way, right? So it's a good principle to keep in mind. Data faster than computation. This is also not true because, again, we talked about cache effects and stuff like that. So if you rely too much on large data, then you're going to have trouble. If you pre-compute data and stuff, it may be actually still slower. So that's not true either. Computation is faster than data. If the converse is not true, maybe the negation of it is true, right? So that's also not true, right? Clearly, right? We can find many cases. So after all, I could say you should have one intuition in mind when doing optimization. I should time this stuff. See what happens, right? I should time this. This is my favorite quote from a living classic. Measuring gives you a leg up on experts who are too smart to measure. The house goes down because of the laughter going on in this cinema here. There's a riot going on. This is awesome. Yes, thank you very much. This was great. Okay, so I'm not kidding. This is for real. So if you measure, you're going to consistently outdo and outperform and destroy those experts who have great intuition and they are too smart to measure. Okay. Now, we want to benchmark for speed, and our goal is to estimate the speed of some algorithm. And we want to also clarify what we're not looking at measuring. We don't want the framework overheads, like the looping and whatever. Clock resolution, we don't care for that. Vagaries, doing the measurements, noise, whatever. Unrelated overheads, setup and cleanup work. We don't want to measure these. We just want to measure some specific piece of code. Now, so if you look at the time measured, it's going to consist of, it's going to be a sum of different timings. And one is what you measure. T is what you're looking at. So T is what the time you want to estimate. TQ is the quantization noise. What's the quantization noise? Sound bites. Yell at me. I know in the last row there's like a few geniuses there with like IQ 170 who maybe they say something but I never hear them. It always happens in the last row. There's like the smartest guys. So what's quantization noise? Quantization. The resolution, yes, thank you. The resolution of the clock is not infinite, so it has like, a few microseconds or whatnot, right? And you can't measure anything that's smaller than that. And you can't measure anything that's not a multiple of that. This is the quantization noise, okay? So we're looking at quantization noise, and we have also things like time added by a variety of noise sources, interrupts, networking, what have you, going on in the computer. We have some overhead time added by the measuring and everything. And now let me kind of just make a remark here. So I have this time, which is a sum of like 4 components, and we're measuring it. And let's say we measure like, 500 times, or 1,000 times, or 1,000,000 times, and we gather different numbers. What mathematical function do you apply to estimate T at its best? Yell at me. Average. Any other ideas? Median. That's a smart guy. Median is better than average, right? Anything else? Average, median, what else? Sum doesn't work, right? Nobody said that. I'm just throwing things at you to kind of confuse you. So sum is not gonna, right? What else? Huh? Maximum. Minimum. Wow, this is awesome. I have like so many choices now. All right. Let me add one to the mix. Mode. What's mode? Mode, the mode of a distribution. The mode is where you have the most density of measurements. Like, the most frequent numbers are going to concentrate somewhere in some place, and that's the mode, is where you measure the most frequent data, right? So mode is actually a good thing to measure, to collect after gathering many measurements. And there's something interesting. So I went with this theory, with this hypothesis. I said, at Facebook we have, they have, I don't work there any longer, but at Facebook there's a benchmark framework, which I partially wrote. I think they got rid of it and once I left the company. So like, whoa, we got rid of that guy. So there's this benchmark framework, and there's a discussion, and we should take the mode. So measure a number of times and take the mode of the distribution. And I measured something very interesting. So I wrote like, it's kind of mode is not easy. It takes like 50 lines of code to math and stuff to kind of implement it. So I kind of sat down and implemented the mode and measured many times different pieces of code. And I made a startling discovery, which is what I suspect. I had an intuition about it, my friends. I'm not kidding. I'm not lying here. The more you measure, the more the mode goes to the minimum. So if you do an infinite measurements, the mode is going to be the minimum. That's my conjecture here. And there is a reason for that. You see this equation here, very simple. The time is a sum of times. So look at the sum here. Time measure is like this time plus that time plus that time plus that time. You could argue that quantization noise is sort of has some, it goes flat for a while. So it's like this. It's like a stairs, right? So that's the quantization noise. But in essence, all of these noises are additive. They add to the time. They never decrease the time. There's no way you could artificially make something faster than it is by introducing noise. All noise is additive. For example, like this TN noise. Oh, sorry. Yeah. Okay. So for example, like this. Jesus. Sorry, guys. Okay. Right. I'm looking for this indicator button, the laser button, which nobody sees, right? I can hardly see it. So I'm pointing to TN, by the way. So whenever I point, I'm going to also use my finger and kind of say, that's TN that I'm looking at. And that noise, many people model as Gaussian. It's not Gaussian, it's half a Gaussian, because it can't be negative. It can't be negative. It's additive, right? So looking at adding different times, and all noise adds some more time to the experiment. So essentially, like the cleanest experiment you can ever get is the minimum that you get. There's an exception. What's the exception? The guy with the max there, I'm sure you have something in mind. There's relevance to the maximum too. Loud. Worst case scenario. We care about that sometimes, not always, but sometimes. And there's actually a subsystem which is notorious for that kind of real-time systems. Yes, but more specifically, networking. Because you have the exponential backoff, you have there's a big difference between like you got really lucky and you got really unlucky. And in networking, you want to actually measure like P90, things like 90% of my accesses, how fast were they, right? How much time it took. So I'm not going to do networking here, so I'm going to go with a minimum. So whenever I measure speed outside special cases, take the minimum is the safest. All noise is additive, all right? Okay, I hope I convinced you of that. And let's look how to eliminate different sources of noise here. So we have the quantization noise, which is the resolution of the clock. And the simple thing is you simply run the same experiment many times, and you measure the sum, and then you divide by the counter, right? That's fine. So this is a kind of a classic, right? You don't measure like 5 nanoseconds thing. You measure like a billion of these, and then you divide by the counter there, Imax. That's great. There's a bunch of other noise, and what you do is you measure in epochs. So again, you take the minimum of everything and you save it, and you have for each epoch you measure the time, and then you measure certain epochs and you take the minimum of each epoch. Notice that here, don't do the minimum. Let me go back. So here you don't do the minimum. You do like the average. You divide by the number. But here you do take the minimum for all epochs. It's different, right? Excellent. Oops. All right. Once I fell off a stage. I'm not kidding. I fell off a stage, and my first words were, "I'm all right." I was like down, lying on my back, and I'm all right. I think it's on YouTube somewhere. So if you're looking for fun, all right, so as I said, there's exceptions to this, like networking, live locking and deadlocking. These are exceptions to taking the minimum. But generally speaking, the minimum should be the first in our mind when you're looking at benchmarks. The vast majority of people take the average, which is the completely wrong thing to do. Because if you take the average, there's always going to be 5 outliers. The cache was really cold, something happened, the setup of the experiment was just starting. There's something extra there, and you got one timing that's 10 times higher than the usual. And you're going to put that in the average, and it's going to dominate everything. It's going to make your timings out of whack. So don't take the average. If there's one thing you take out of this particular hour, that shouldn't be the average. All right? Take the minimum of my talk. All right? Take the minimum here. Don't take the average. All right. So, great. Now we have overhead noise. So we have this loop here going on, and it does things. And we want to measure here. So one good thing to do is to just measure the loop itself and subtract it from the experiment running time. What mistake am I making here? This code is not going to do well. Yes, shout, yell, loud, last row. Optimization. It's going to eliminate the whole goddamn loop, right? It's going to, I'm not kidding. So the code generator is going to be start clock, measure time. Because the compiler is going to be smart enough, there's no compiler today that I know of that's not going to eliminate that loop entirely. So what do you do then, friends? Zero what? Compile with no optimizations. No, you don't want to do that, because if you compile with no optimizations, like, for example, like these pluses, all this code generator is going to be different from the code measured with full optimizations. So it's an interesting thought, but I don't think it's the right solution. What? Put something inside the loop so you fool the compiler into thinking you're using it, right? Other ideas? Volatile. Volatile is guaranteed to be, gosh, I don't need to do anything. You know everything. So my role here is just to channel your energies. So yeah, use volatile, because that's going to be guaranteed to be visible, so the compiler can't optimize it away. There's one more thought here. Assembler. Go to assembler and do something, because it's always an answer, right? Put something in the loop, like that goes with the measure inside the loop. Okay. Well, I'm very happy to say I have a bit of everything here. So I have volatile, awesome, and it's also underlined. It's not easy to do that with LaTeX, and notice that it's underlined and blue, and it was not easy. Okay, I take pride of it's not only my biggest slide, it's my bluest volatile underlined keyword, right? So we have this volatile thing. And that's not actually good, because this is going to generate very different code from non-volatile loops. So that's not a great solution, actually. A better solution involves some assembler, although it doesn't look like nothing. This is, let me put it this way. This is GCC's way of saying, I don't want you to optimize this loop away, right? So essentially say ASM volatile means it can't be eliminated, and you put nothing in there, but it's there. So GCC is not going to optimize that away. I don't know of an equivalent for Windows, actually. But GCC and the Clang both recognize this stuff. So by the way, who's here? Like, what compiler do you C++? All right. What compiler, like GCC on Linux? Or no, GCC period on any system? Clang, MSVC. All right. So I don't know, 50, right? That was the ratio I measured there with scientific clarity. Okay. So this is the way you do it in GCC and Clang, and there's a different problem here that's also not using, using or not using the result of a function. So you have a function and you call it and you want to benchmark it a number of times, but you're not using the result. So again, the compiler may say, you know what, this function is never actually used, so let me optimize that away. So to clarify that, you implement a function, which I suggestively call do not optimize away. It's a cry for peace with the compiler, because the compiler wants to optimize, I want it to not be optimized. And again, this is, where was I? This is GCC's way of saying, this particular piece of data, please do not, I'm taking the address of it and in a way that you can't understand. And a way that you can't understand is spelled in GCC ASM volatile and all that good stuff. It means I'm reading the address of the data. Right? And of course, oh, sorry, I thought this is a, man. Oh, I'm missing a slide here. Okay, so we have this primitive here which says, do not optimize the way I'm taking the address of this particular piece of data, and that's how you spell it. And there's a converse to that, which is, okay, gosh. So I'm going to spend the rest of my time here. That is closer to the station. All right, and I'm going to, at the end of a measurement, I'm going to say, you know what, I'm going to clobber the entire memory. So do not make any assumption about the next iteration. So that's another primitive that's very useful when measuring. So this means I'm touching all the memory in ways that the compiler can't understand. So do not optimize things. Great. There's a more portable way, and that works on Windows as well. You can say, for example, you can get the PID of the process, and that's never going to be 1. Unless you're a kernel guy and you're doing kernel development, because the first process ever starting has the PID 1. But that's never going to be the case in a usual application. So this test is not going to pass. But the compiler can't know that. So then you say, I'm going to take the address of the data, and I'm going to call putchar. Why putchar? Because I/O routines are always visible. Right? So volatile data and calls to I/O routines are always visible. So the compiler treats them specially. So they're special to the compiler. So that's why I'm using putchar here. Great, even though the code is not executed. So, all right, so, well, to use this guy, we're going to do something like I'm going to measure ASCII to integer and do not optimize away the result, and all works well. So keep in mind these routines here, these primitives. There's also a discussion about, what clock primitives to use, and there's a number of them. On Windows, you have query performance counter, which is sort of the best all around. It's dedicated for this kind of stuff. On Linux, there's like portability issues and stuff, so make sure you use a kernel that's fairly recent because it used to be broken and that kind of stuff. So clock get time of clock real time is the best you can use. And there's more conservative, low resolution, low fluctuation timers, which are time get time and get time of day. And there's also a CPU specific instruction which gives you how many cycles have been spent since the boot of the computer. So it gives you a counter that keeps on increasing. And what do I mean here by CPU jumping? So I have a counter for each core that tells me how many cycles have been spent since the start of since the computer was booted. And there's a risk to measuring that. Frequency changes. So I don't know exactly how long each cycle takes, but maybe if I count the cycles, I'm still fine because fewer cycles means faster code. But there's a larger risk here. All right, so I got the right answer from row 1. So what was the middle row saying? Huh? Interruptions. Interrupts. Well, what do the interrupts cause? They're going to change that. But if I take the minimum, maybe I have a chance to. That's not the biggest. It's a risk. It's not the biggest one. The biggest risk is what the first row said, which was you may start a routine on one core and then it on another because of the thread, the thread scheduling may do it that way, right? So you can start on one CPU and then you're different. And you measure you're measuring timings for different CPUs physically. So you gotta make sure that you set a thread affinity of the measurement to a specific physical CPU. Otherwise, you're gonna get wrong timings. So there's no perfect answer here. There's a bunch of variables to take into account. But there are a number of good frameworks. So Facebook is public. So Facebook has an open source benchmarking framework. Just Google for Facebook Folly. It's a library by Facebook, and it has includes this benchmark code. Google Benchmark also has quite sophisticated benchmarking tools, and it's also public. So I recommend those. But there's something that I noticed that distinguishes a good engineer from a not so good engineer. Of course, we're all good here, so I shouldn't be speaking about this. So make sure you convey this to your coworkers. Okay, so you're gonna tell them, I told them so. Okay, I know you're the best. You're here by choice, right? You're not like, so you know all this stuff, but make sure that you spread it along. So I noticed that many people measure without baselines. And they don't know what the baseline is. They don't choose good baselines, and their measurements are wrong because of that. So baseline is your starting point. It's a classic, naive, established, commonly accepted, well-known solution to what you're benchmarking. For example, it could be your previous edition, whatever you had in the past, before you started to optimize, you can use it as your baseline. If you want to write a sort algorithm, use sort as a baseline. If you do I/O, you can choose I/O streams. Although that's such an easy baseline, you're going to destroy it because I/O streams are very slow. Did you know that? I/O streams? If you want speed, I/O streams are not the answer. We're going to have numbers in the later talk about I/O streams. If you want to parse numbers, you can use scanf as a baseline. So always start with a baseline because it's going to tell me nothing if you say, I scanned 1,000,000 integers in 100 microseconds, and I'm like, okay, so what's your, where did you start from? What does scanf do? That kind of stuff, right? So always choose good baselines. There's no way around it. You gotta make sure you choose good baselines in all circumstances. There's no measurement without a baseline. And when you measure, take the measurement, subtract the baseline, and that's your number. If it's negative, you have been pessimizing your software. Pessimization is the process that's opposite to optimization, right? It's a word, right? It's not in the dictionary, but we can make it up. I'm sure you understand. So always choose good baselines. A bad example. I sorted this many floats in this much time. What machine did you use? What was the distribution of the floats? Because maybe they're like uniformly random chosen, and that's very different from Gaussian floats or constant floats or whatever. So that's a bad way to speak about things. This is better. If you have Gaussianly distributed floats and use quicksort, you're going to have 25% improvement in speed compared to heap sort. So by the way, this is like made up. I'm not sure what, but this is a good statement to make. It's a good measurement to make, right? And even better, you have, I've seen this in a benchmark. You have multiple sort methods, multiple data sizes, and you have like multiple dimensions along which you measure, and there's always a baseline to compare against. So that's awesome. Great. So there'll be something to say about differential timing. Essentially, it has to do with layout of the code. So you arrange your code such that you have your baseline, and again the baseline. So I have baseline, measure both. And then you say baseline, I'm substituting my code instead of the second baseline, and I'm measuring both. And that's going to automatically cancel some noise. And then you take the simple formula and you got it. So that's going to make sure that essentially you just take the baseline and the baseline again, and then you rip away the baseline, you put your own code instead of the second, and you make the two experiments. And it's impossible to, you see very small differences there. It's a very good technique, differential. All right, so Things to be aware of. I shouldn't be speaking about this kind of stuff because you shouldn't measure the speed of your debug build, right? Debug build. You don't, this like, everybody should be like, oh, of course not. I don't see anything, by the way. I'm seeing like these like Gestapo style like lights in my eyes, like the interrogation lights. And I'm looking at you, but I'm seeing nothing. I'm seeing like lights. That's, probably it's like to extract maximum information from me. That's the purpose of the lights. So I'm telling you everything I know, okay? There's nothing that I know that I'm not going to say. So, great. Well, so nobody should be measuring the speed of debug builds. It's not relevant to anyone. Don't do it. Different setup. This is a classic. Like people do things like they measure the baseline and then immediately they put the measured code without doing any cleanup or any clubbering of the memory. And that's going to be different. That's why in the differential time you put the baseline and the baseline twice, and then you substitute the baseline. So you have the same condition for the second round of the baseline. But many people just put a baseline and then put a measured. And for example, by the time the baseline has run, the memory configuration, the memory allocator is messed up completely because it has allocated memory and done things. So it's a very different configuration. And then they say, oh, this is faster. But if you reverse the two, actually the other is going to be faster, which is weird. So make sure you don't do that. Don't do the sequencing wrong. Or if you do it differentially. I've noticed a bunch of benchmarks that end up measuring like how fast malloc is or how fast printf is, regardless of what they wanted to measure. I'm seeing like a lot of conclusions, the wrong conclusions. They measure like a mixture, and then they conclude they improved one, but actually they improved the other, which was not measured. And last, which is interesting, I've seen a lot of folks who do this. They optimize for a rare case at the cost of everything else, and they choose a test data to be the rare case. It's a perfect crime. Yeah, because the numbers are there. It's just that the data is wrong. For example, so there's this, I found this on Stack Overflow. And the question was this. I am sorting data that is already sorted. I'm sorting data that's already sorted. And how come sorting is slower than just is sorted? Is sorted? It's a Boolean. Is sorted in the C++ standard library. Is underscore sorted. It goes to the thing and makes sure it's sorted. It returns a Boolean, right? And essentially the premise here was if the array is already sorted, then is sorted is going to return true, and the time run for is sorted should be the same as std sort, because std sort doesn't need to do anything. However, it was slower. And the question was, why doesn't the sort routine in the first line, why doesn't he call it sorted? And if it's sorted, it has nothing to do. What's the fallacy here? It makes no sense. It's a very rare case. I hear all the good answers, right? So very little of the data is 100% sorted. Maybe a lot of data is already almost sorted. It's a bit sorted. It has a sort of component to it, right? There's structure in the data. But it's going to be very rarely 100% sorted. And of course, inserting that time is going to make the algorithm slower for everything that's not completely sorted already. So that'll be a bad thing, right? All right. So I'm going to discuss here a few techniques of optimizations that are going to last you for a good few years, which is a long having time in this business. Okay? They work for most silicon-based von Neumann machines of today, because there's things to them that have to do with math, and there's things to do that have with realities of physics in the computer. And those are unlikely to change, especially math, right? Like the math is going to be like awesomely there. Like Taylor series is going to be Taylor series for all eternity, right? So I'm going to teach these kind of things as opposed to little tricks that work today and they're not going to work like in a year from now. And we have a few generalities here: storage numbers, strength reduction, and minimizing indirect writes. These are the topics that I'm going to focus on. And in general, if you have the option, prefer static linking to dynamic linking of your code, and prefer position-dependent code to position-independent code. Why static linking versus dynamic linking? Shout, yell, whole program optimization, yell, local jumps, yell, inlining. So there are a number of optimizations available for static linking that are not available to dynamic linking. And the simplest is that depending on the architecture, the cost of the static call itself is going to be smaller, right? So also position-independent code turns out to be a few percent slower than position-dependent code. So there's an option, fpic, in GNU, and I'm sure there's something in Visual Studio. It's going to generate different code depending on that option. So prefer position-dependent code on today's. This is not going to be very. It's not going to last for a long time. I'm not sure. So this may not be the most important thing. Prefer 64-bit code and 32-bit data. The reason for 64-bit code being faster is interesting. It turns out that in hardware, all optimization effort goes to the newer code, which is a 64-bit code. So for a sort of a psychological and sociological reason, it turns out that the 32-bit code is just in support mode. They don't care about it anymore. So it runs slower. And the 64-bit code is where the action happens, and the engineering teams at Intel are working on that kind of stuff. And so 64-bit code is going to be like the best supported in the compiler for speed. However, 32-bit data is great because, there's a number of reasons, some of which we're going to discuss later today. But the simplest reason is it's smaller. And because it's smaller, it puts less pressure on the cache subsystem. So awesome. Prefer 32-bit array indexing to pointers. So this is this has been like every 5 years this changes. So I got to say that I'm telling you this, and 5 years from now, I'm going to be invited again. Thank you very much. And I'm going to say, prefer pointers to array indexes because they're faster. It turns out that today, it's better to do array indexing. Prefer this guy to that guy. Why do you think so? They don't have the same semantics. But my point is, if you can write your code, if you have the choice, prefer this guy to that guy. Why do you think so? Why is this like the I is an integer, A is an array, and I'm telling you to write this guy, not that guy. I++ is faster. Why is it faster? You gotta yell and temporary. No, I is in an integer. So don't think iterators and stuff. Huh? It's already computed. Interesting. No, it kind of is hitting, it's getting there, yes, but clear. Yes. No sequence point. It's even close, it's hot. What's the point here? Data dependency, thank you. The first row is always the best, awesome. All right, so there's fewer data dependencies in this guy than in that guy. Why? Because here, you can increment I simultaneously with fetching the array element. Simultaneously, you can do them, so you can just fork the code that does that and the code that's exactly what happens actually. In the CPU, there's different units dedicated for decoding addresses and for incrementing things. Registers, it turns out. I is going to be in a register ultimately. So it uses more hardware and it goes in parallel. Here, you can't do that. It doesn't work that way. Here you're going to say, first increment I, and then have a coffee, and then fetch me the element of the array. Right? No sugar, please. Right? So it's a sequence. It's a number of operations that must occur in sequence. But the first guy is not a sequence. There's no sequence. It's like, fetch me the array and simultaneously increment the index. Of course, there's not one time I talk about this and after like a week I get an email from someone who says, I wrote that and it didn't improve my speed. This is not a guarantee, folks. I'm not legally bound for this, okay? I'm not promising anything. I'm just saying prefer it because you may get some mileage out of that stuff, but it's not guaranteed. Okay? Don't write me email about that. Okay? So if you change the code, then it's also different semantics. So one is incrementing before and one is incrementing after. So, if you rearrange your code and you don't notice an improvement, maybe that wasn't the dominating factor there. So don't kill the messenger here. Okay? All right. So, prefer regular memory access patterns. What's the keyword here? Yell at me. Shout. Cache. No cache. Whoever said cache, wrong. Completely wrong. I was kidding. I'm making all these jokes, and I'm hoping you guys are like, oh, that was funny. That I could see the humor in that thing there. But then it's like silence. It's like maybe I offended someone. Maybe they think they should leave the room right now. Whoever said cache, get out of here, right? So no, don't get out of here. Stay here in the hot. Is it hot, right? Are my ears red? Okay. So what's the keyword? Your action, no, that's not a keyword, it's a sentence. Keyword. Prediction. It's close, but it's not the keyword. Locality, no. Cache, don't say cache ever again in this. What's the keyword? Prefetching. Prefetching. Prefetching means the cache subsystem fetches blocks of memory, and if it detects that you're iterating forward, it's going to prefetch while you're doing work. It's going to separately, in parallel, simultaneously, literally, prefetch memory into the cache because it anticipates you're going to continue looping through memory forward. And until 5 years ago, that was it. But now it's also prefetching for iterating backwards. It also detects that thing, that pattern, and it also prefetches from behind you, right, from lower addresses. And that can make a huge difference because it's literally work done in parallel with your own work. So you don't need to wait at all. So prefetching is huge. Minimize flow, avoid data dependencies. So flow and dependencies are the largest enemies of today's architectures. Flow means jumps, and the more unpredictable the jump is, the worse you get, right? Data dependencies means you can't have instruction level parallelism, which we're going to discuss next. All right. So with storage, there's a sort of a hierarchy here. Immutable data is the best. Use static const. Use the stack for everything you can. It's really hot. It's the hottest place on earth is the stack. It's awesome, right? You have zero cost addressing is like a field in a struct or a class. Is real quick. For globals, I told you in the beginning that I don't want to teach you that globals are good. Globals are bad. And actually for more reasons than you may think. Globals are also bad because they pessimize everything around them. Because whenever you do anything, the compiler must assume the global has been seen by all other functions and must reload it from memory. So that's pretty bad. Globals work very well against and registering variables, putting variables in registers automatically. And actually, globals are slow to get to, which is weird. For example, it takes like on OS X, to get a thread local piece of data, you call a function essentially. So it's as bad as a function call. All right. Integrals. Not everybody is going to like this, but you should prefer 32-bit integers. And there's a reason for that, which is yes. Always reads bits. No, I didn't understand. So yeah, just shout as strong as you can, as loud as you can. Why is 32-bit integers better than 64-bit? There's a very specific reason. They're smaller. Math, 64 greater than 32. It's awesome. They're smaller, but even if you don't have an array of a million of those, there's still a very good reason for 32-bit is the sweet spot. Because the ALU, the arithmetic logic unit inside the CPU, can do 164 operation at a time or two 32-bit operations using the same hardware and the same bus, right? Because it gets like 64 bit of data and then it's like two integers and it uses one and it uses another in parallel. So actually you can double the speed of things, of operations, by using 32-bit integers instead of 64-bit. And please notice that on many CPUs of today, if you think that smaller is better, like smaller, 32-bit is maybe, I'm okay with 16, and I'm okay with 8. Actually, all of those do math in 32-bit, so there's no further optimization there. So use 32-bit is the sweet spot. Prefer unsigned to sign, which is faster. Unsigned is a bit faster, but converting unsigned to floating point is probably the slowest of all conversions. And apply the law of small numbers. Most numbers are small. So if you find any optimizations that work great for numbers up to 8 or 10 or 1,000, then use it. Because many numbers in day-to-day operations are small. Okay. All right. For floating point, there are a number of interesting issues I wanted to underline. One is that double precision, single precision, they're just as fast. They just throw hardware at it, it's just as fast. Even 80-bit precision extended is just a bit slower. It's not a lot slower. But do not mix them because there's going to be conversions back and forth, and there's going to be extra effort to accommodate conversions. So inside the CPU, you have more than one units for manipulating floating point numbers, which is important because you can do them in parallel. And there's SSE, which I'm not going to discuss today. And with regard to conversions from floating point to any integral, it's the more expensive operation. All right. So I'm going to discuss here a topic that I find very interesting, which is called strength reduction. And it goes like this. As a matter of principle, you want to use the operations of minimum strength when optimizing a function. So you want to make sure you use the minimum strength needed because the stronger operations are the more costly ones. And to make sure that we get the hierarchy right, we have the cheapest are comparisons. You can think of them as less than one cycle. Add, subtract, bit operations, and shift are one cycle each. Even on 64-bit. So that was news in 2004 when, I think it was that year when one cycle 64-bit add operation became mainstream. So today you can say it's just one cycle whether it's 64-bit or 32. Of course, if the integer is 32-bit, you can count on doing two of those in parallel, or more. So it's actually better. But essentially, you can think of all of these operations on integers. They cost you one cycle each. Floating point, add and subtract, they're done by separate hardware, and they're very fast. It turns out. What follows then more costly is like the integer multiplication and floating point. And the more expensive ones are the floating point division and remainder. And the worst of the pack are integral division and remainder. The worst, the slowest operations. Slower than floating point. Who knew this entering this room? No. Who didn't know this entering this room? Okay, now you have the courage, right? So this is like one of the surprising results, and it has reason for it. Why do you think it's cheaper to do floating point division than integral division? Thoughts, ideas? Integer gets, no, there's no conversion. It's just, it's primitive operation in integrals. Oh, too many. Yes? In floating point, you do one by and you multiply. I don't think they do it that way, but that's not the real answer. There is a very profound answer to this. As soon as I said profound, it's like nobody's like, you know what? I don't have anything profound to say right now. I'm not. There is a profound reason, which is the following. What's the format of floating point numbers? You have the mantissa and you have the exponent, right? And the exponent is when you divide things. What do you do with the exponent? You do a subtraction of the exponent. So the exponential format in which the floating point numbers are stored is already friendly to multiplication and to division, because it's one cycle to do a subtraction there. And then you have the mantissa, and you can do approximations, and you can have imprecisions and things, which you can't afford for integers. For integers, division is the worst, because it's the most unnatural, philosophically speaking. There's never in nature the division by 17. Right? There's no molecule, there's no cell organism in there that says, you know what, I'm going to divide myself into 17 little molecule cells there. There's never the case. There's one division that's relevant to nature, and that is division by 2. That's it. In nature, it's division by 2 and nothing else. 3 is already like out of whack. It's like, what the hell is that? Right? So, there's a lot of stories about this and a lot of deep thoughts about this. Division is search. Division is not an operation, it's a search. I'm guessing what the result would be, because when you do the multiplication is easy. It's like natural. I'm multiplying things, awesome, and there's a bunch of, bunnies multiplying themselves, you get Fibonacci. Right? That's the Fibonacci is like with bunnies, with rabbits. They wanted to estimate the population of rabbits if they do what rabbits do, right? For a long time. So, oh my God, there's a large number. We got to kill our rabbits right now. Send them to Australia, right? So, division in integers is unnatural, and because it's unnatural, it's difficult and it's slow. It's a search operation, right? And for floating points, it's slightly better because they're already in nice format for division. But as soon as you have a division there with an integer, you say, I should optimize this stuff because division is just very slow. To wit, I have a division right here in the do loop. What's the do loop doing? I'm having a very simple example. It needs to fit on one big slide. Digits 10. Compute the number of digits in a number. Very easy. It's a classic, like you've done it in college, and maybe you ask it at interviews and that kind of stuff, right? So, well, what do? Well, we divide the value by 10 and we increment the number of digits until we get to 0, and at that point we have the result. And it uses integral division. My question to you here is, think about how to optimize this function. Optimize this. Ideas, keywords, shout. Logarithm. Use that logarithm instruction that's really slow, right? That's a good start. Yes. Huh? No, I can't hear it. No, you gotta. Okay, I assume that's great because it was longer, but I couldn't understand a thing. So keywords. Shout keywords. Double. Use a double because we just talked about this. That's going to get you 5%. I'm looking at 5 times, not 5%. I'm looking at major improvements here. Divide by 10 and then compare. Multiply by 10. Take the 1 and... Yeah. Awesome. Yes, so take it from the other side. You kind of start from 1 and kind of multiply 110, 100, and so on, and compare with what you got. If it gets greater, you're done, and you have the digits. Awesome idea. I didn't measure that, but it's not on my slide, but it's a good idea. Thanks. Whenever I give this talk, I get no ideas for the next one. I'm not kidding. Thank you. Other ideas? Let's see. Well, let's look at this speed. So we want to be as up high on the speed hierarchy as we can. And actually, subtraction is kind of here, but this was a great idea because it uses comparisons, right, and multiplications. But here's an idea. I'm going to use only comparisons for the most part. Okay, here's my idea. It's funny. You're laughing now, but I tried to make you laugh like all this time with no success. And now this is not a joke, folks. It's for real. This is real code. It's supposed to be serious. You're supposed to be like, right? Oh, okay, that's interesting. Oh, good stuff. All right. So, I have a meta tip for you, because I noticed that many people, when they want to optimize a loop, they start with writing the loop down. The for ei equals 0 to n do something, right? ei plus plus. So they write the loop structure first. You don't want to start with that. Whenever you want to optimize, you always start with an infinite loop. Although it's paradoxical because that's the longest loop you can write. It's infinite. It's going to take forever. But the infinite loop gives you inside the loop. So it's the fastest code generally because it's going to have an unconditional jump at the end. And inside the loop, you get to organize your computation with early exit, break, continue, whatever. You get to organize computation at its best. And this is no exception. It would be difficult to rewrite this code with a structured loop. So that's why I start with a for that's infinite. Okay? So I start with this infinite loop, and I say, well, is my value less than 10? The small number assumption, the first test I'm doing is whether the number is small so I can get rid of it and get out early. So for all numbers that are like really small, like 1 to 10, 0 to 9, I get out in one test. I'm out of here. I have the right result. I'm returning 1. And I'm testing again 100 and so on. And if I made it to 10,000 before and I didn't find the answer, then I'm going to skip by 4 orders of magnitude. I divide by 10,000, and then I'm going to increment the result by 4. And then I continue. Okay? Yes, yell, shout. Why did I stop at 4? Because I measured. I'm not kidding. If you put more, the code becomes too big. The loop gets out of the cache line. It's slower. Right? So and by the way, this may look to some of you like loop unrolling. It's not unrolling. This is not loop unrolling. Loop unrolling, you do the same thing over and over again. Right? This is not unrolling. So I'm testing 4 of these numbers and then get out. Yes, questions? All right, so we traded off 4 divisions by 10 by 1 division by 10,000. That's going to be presumably faster. We do have more comparisons. We do have more additions like these guys here, the result plus 1, result plus 2, etc. But overall, I'm trading off expensive divisions for cheap comparisons. Okay? Well, do you think this is going to be faster? And by how much? Well, I measured. So looking at very good improvements all over the board. So these are the number of digits in the number up to 20, and this is the relative improvement. 1 means I'm doing as fast as the naive version. Right? 2 means I'm doing twice as fast. So we look at very hefty improvements, like 4 or 5 times improvement. Okay? Now, there's a number of oddities here in this graph. For example, there's a drop-off between 8 and 9. Why do you think so? That's a division right there, right? And then I'm going to walk here, falling into this trap here. We have, like, again, 12, 13, another division. Every 4 digits, right? Let's see, 7, 16. Wow, this is amazing. Science works. Wow. Okay, so this can be explained easily, right? These results. Great. There's a pro version which uses likely. So it turns out you can inform the compiler that to expect a result of a test more than the other. And you put that in a macro, and you call likely. So you expect that the numbers are small, and the compiler is going to generate code that's going to do fewer jumps over the expected cases. It turns out this generates a lot smaller code. In micro benchmarks, you're not going to see a difference, but you're going to see a difference if you put that in a larger system because the code is smaller. So, interesting. The likely macro is defined on GNU as a built-in expect. Built-in. It's an intrinsic. And you expect that likely is 1, and you expect that unlikely is 0. So you use these guys. And we have a good routine for computing the completely irrelevant thing, but I'm going to use it later. Now, the second topic, which is interesting to us, let me see, we have like 15 minutes left. Okay, great. So my point here, we have like 15 minutes to go, and I know you're tired, and I know it's like morning, and it's unusual for you to kind of sit in a hot room for a whole day. But my plan here is to use these 15 minutes in a way that I'm going to finish on a cliffhanger. And okay, oh my God, I got to see this guy next. I got to see what this guy has to do about whatever comes next, right? So I got to be in his second session there. So I'm going to try to end with a great cliffhanger, and the best solution is, and you're going to find about that in room 4 at 3 o'clock. I don't know. Okay. So my next tip is minimize indirect writes. Indirect writes means writes through a pointer, array element, something that's, that involves an indirection. Okay? And why do I want to minimize that? That has to do with reality in hardware that it's very difficult to optimize in any way. It's very hard to speculate, very difficult to enregister, put in registers, that is. And one very interesting detail is that whenever you write something, it's really a read and a write. Who didn't know this entering this room? I didn't know until like a few months ago. Who knew this when you entered this room? Okay, who's asleep? So the difference is everybody else is like, you know what? I'm not going to raise my hand when this guy asks me what the hell is wrong with him. I'm just sitting here having a good time, hoping for this to finish, have a coffee finally. But a write is really a read followed by write. And here's why. Whenever you transfer data with memory, you don't transfer like a word or a byte or you transfer a cache line. That's 64 bytes. That's the unit of transfer. You don't transfer like a word. You transfer 64 bytes, not bits, bytes. Okay? 8 times more. So if you want to write a word, what's the computer going to do? It's not smart. It's not clever. It's going to this guy wants to write the 6th word in this cache line. All right, so I got to make sure that it can only write the whole cache line. So it doesn't know what's in the rest of the cache line. So first you need to load the cache line, change the word in the cache line, and then write the cache line. There's no other way, because the unit of writing is a cache line. So it reads the whole goddamn cache line, changes whatever it changed in it, and puts it back. So it's a read and a write. It turns out, if you happen to write a whole 64 bytes of data at a time, and so if you write full like 64 bytes, and if those happen to be cache aligned, 64 byte aligned, it turns out that write is going to be twice as fast because there's no more reading. You write the whole cache line at once. And I've seen code in which people insert extra writes that are not used. They put a 0 in there, and they put a comment, do not remove this. It's going to make the code 2 times slower. It's an extra write that makes code faster, and I'm not kidding. Okay, so that's why you should care about this kind of stuff. Minimize indirect writes. All right, so also, whenever you write memory, it's interesting that, again, the computer is not smart. So whenever you write something, even though it was identical to what was there before, it's going to mark a bit that the cache is dirty. So this line of cache is messed up. It's dirty. So whenever you evacuate the cache, whenever you evict the cache to load some fresh memory in, whatever memory is dirty is going to be written back to the main memory, which is a very slow operation. We're looking at hundreds of cycles there. If it's not dirty, it's not going to be written again faster. So the more dirty cache you have, the more writes you need to do, right? Okay, I hope I convinced you. And to wit, we're going to run an experiment here. Let's define a classic routine, which is integer to ASCII. And I have a pointer to the destination as an argument. And I have my value to convert. And essentially, like, this is the classic algorithm. I think they call it the Horner scheme or whatever. And I write the bytes, I write the value, and I divide by 10, and I get always the smallest byte because I get the remainder of the division. So I write the smallest byte first, the smallest digit, and then I get to the largest digit when I stop. And then at the end here, I have a reverse in place sort of code, which is going to reverse the number to put in the right order. Okay? Make sense? Good shape? Okay. Awesome. So this is, again, a sort of a classic routine. So if you look at the implementation on a typical library, it's going to have this kind of pattern. Compute the digits in the wrong, so the reverse order, and then reverse the array. So what bothers me here is, well, two things. One is that we have a lot of divisions by 10, which we know are slow. But the second is, like, we need to do all of these iter swap. We're going to have all these indirect writes here in memory, and we don't like that. We want to eliminate that. Ideas. Optimize this. Optimize this. Yes, loud, really loud. Compute the number of digits first. We just have that routine handy, and we just spend time optimizing it, which is awesome, right? So we could compute the number of digits first, and then we get to write them in the right order because we know when to start. That's great. Oh, sorry, we write them in reverse order. So we write them from right to left. That's a great idea. So let's see how that works. So first line there is going to compute the number of digits, which we just wrote. We have the digits 10 routine. And then we go back, and we essentially write, you see buffer of post minus minus here. So this is our write route, the point at which we're writing in memory. This is the indirect write. And when we're done, we handle the last digit directly. This is like the immediate. Like the first digit in the buffer, you just take 0, the digit 0 plus the value. This is like my value here at this point is guaranteed to be less than 10, right? So with this, we still have divisions by 10, but we don't have the indirect writes caused by the reverse. Well, is this going to be better? What do you think? Let me put it this way. We're doing a gambit here. This is not guaranteed to be better, and I'll explain you why. We're making a bet because digits 10 already goes to the number once. although it's a function call, there's a lot of work going in there, right? It's doing an iterate, it's a loop. So I'm taking a gambit that by doing that loop ahead of time and going through the number twice, I'm still going to have performance improvement because I do fewer indirect writes. And it turns out that gamble is winning. So to summarize, what we wanted to do here is fewer indirect writes array. We have a regular access pattern. We write through the array from right to left. It's going to work really fast on small numbers, and we have fewer data dependencies. So let's see. Wow, this is pretty awesome. And think of this. This is a routine that nobody worked on for like 30 years. Like if you go in any library, like for any language, including like glibc, what have you, they're going to have the classic loop there. And it's going to be, nobody looked at that for a long time. But if you look at it with a fresh eye and you say, you know what, I want to minimize indirect writes, then you do it this way, and it's faster than code that nobody thought can be made faster. And that's remarkable. It's not fantastic, but it is remarkable. You can get like 2x improvements on small numbers, over 2x. So that's great. Could someone explain? So we have like one. So the improvements get smaller for larger numbers. Can anyone explain why? The cache line thing. What else? Let's look at the code again. So for large numbers, the gain is going to be smaller. There's still going to be a gain. It's going to be smaller. What? So the cost of the divisions is going to end up overrunning everything else. You have more divisions going on. Essentially, that's going to be the major cost of what you have. Great. Okay, now, checkpoint. So you can't improve what you can measure. You'd be amazed how many people think that's not the case. And to kind of make that stronger, you can't measure what you don't measure. Okay? So make sure you measure everything. Whenever you want to improve code, you got to make sure that you measure everything. Second point, always choose a good baseline. This is like, again, if you take anything away from these, from this particular talk, if you take anything, just baselines is your friend. It's just amazing how few people actually use baselines. Do use baselines. They're a friend. I'm going to tell you if you're doing better than what you already had. To wit, there's a paper in the early 2000s about custom memory allocators. And a number of applications write their own malloc, is what I'm saying. A number of large projects, they decided, this is a big project, we got to write our own malloc. And what the guy did, Emery Berger, what the guy did was he eliminated that and he used the built-in malloc. Of 8 benchmarks, like 7 were faster with the built-in malloc. I'm not kidding. And that you're supposed to laugh, and I was supposed to say I'm not kidding, and that's how it goes here. Right? So it turns out if you replaced code that has been carefully written by experts to improve memory allocation with the built-in code, it turns out you get faster. So those folks spent time on making code slower, which is a very interesting concept. They made money by making code slower, right? Which is, it's one of those things, right? Okay, so always choose good baselines and optimize code judiciously. Great. So as I promised, we're going to move forward toward the cliffhanger. What time is it? Oh, like 3 minutes. Awesome. Okay, this is going to be a great cliffhanger. So, no, that's not it yet. So I'm showing this to you. I don't expect you to see it, but this is like an Intel CPU, and what I want to so essentially there's a data flow going from the top to the bottom. That's sort of the basic stuff. Enters from above, it goes like messed up, and it gets vomited by the end here, right? That's the digestive system of the Intel CPU, okay? No offense intended to that fine company, okay? So, I want to attract your attention to where is the digestive system the thickest? Where's the belly? Where is the pipeline the thickest? You don't need to see much, but just tell me, like, it's up, where is it? Here, right? This is the belly here. This is the thickest part where most things are happening in parallel. What's here? The ALU, arithmetic logic. This is where computation happens. Computers are essentially good at computing because of this. No, I'm not kidding. Because many people are, what are computers good at? And my mom would say, I can write you email. And what she doesn't know is that all of it is just computing, doing like additions and shifts and subtraction. It's amazing you can use those things to write emails to your son over the ocean, right? That kind of, but it all starts here. This is where the action happens. And in particular, it happens in this unit here, which is the arithmetic and logic unit. And here's where it happens, most of it in parallel, which is amazing because this is only one core. Few people know that actually your CPUs are doing in parallel things that you think are sequential, because they have logic here. That pink thing is called the reservation station, and it allocates operations as parallel as possible. And it turns out they get a 4.2x improvement on average on serial code. So even though your code is serial, it gets parallels 4 ways automatically. So, wow, this is something. So, we better use this stuff as good as we can because there's a lot to gain here. And let me point this out. This is called instruction level parallelism. So the more instruction level parallelism your code has, the more you get to use of these things in parallel, and otherwise they stay dark. They're not used. And they're dark like forever. You can't come later and say, oh, actually I meant to make this more faster, more parallel, more whatever. So the only thing you can is buy more machines of which you're going to use a fraction of. Right? Because once you lose this parallelism here at this level, it's lost forever. That silicon is going to stay dark forever if you don't use it. So that's why I call this the forgotten parallelism. Everybody forgot about it because everybody thinks they're going to throw more hardware at the problem. But actually, if you use this well, you're going to have multiplication factors in your speed with lesser hardware. So you can do more things with more hardware, etc. All right. So how do we use those many ALUs? And let me kind of point out here. So we have, this is a floating point unit. This is an SSC floating point unit. This is an integer unit. These are address computation units. And you can do a lot of stuff with these things. For example, you can do an addition and another addition and a multiplication simultaneously on floating point numbers, which is amazing. You can do a lot of things. All right. So there's a lot of factors that are already using and fostering ILP. Pipelining, superscalar, out of order, all of these keywords, they do ILP. So there's a lot of stuff dedicated to them. And to go for the high, this is a great cliffhanger. I'm going to explain in the next class that if you want better instruction level parallelism, all you need to do is have fewer data dependencies. Thanks very much. See you later.